Hello everyone, and welcome back to the General Chemistry Laboratory. I hope you all are safe and sound at home and are well and are able to switch to this unexpected, abrupt mode of teaching and learning remotely. Today we're going to cover the experiment that you would be doing this week, which is determining the rate law of the reaction between sodium hydroxide and crystal violet. And I'm going to go over the notes like I typically would. The only difference would be, instead of actually performing the experiment, you will be receiving an email from your TA, which will contain 2 data files in Excel that will contain experimental data, and I will explain today what you are going to do with those data, and then you'll be submitting your lab report back to your TA, and I will explain what that report must entail. So let's go ahead and talk about the reaction and what we're trying to do here. Reaction involves a dye called crystal violet. I brought a bottle of it that you would have been using if you were here. So this is the solution. As you can see, it has bright purple color, and concentration of this solution is 1.5 times 10 to negative fifth. So it's a very dilute solution, and yet the color is very, very bright, which you recall, if our solution is colored, it means we can measure its absorbance. And by measuring absorbance, we can follow change in concentration. This is an important point that I will come back to shortly. So the reaction is going to involve crystal violet and sodium hydroxide. The reaction is called bleaching because as time progresses, the dye's concentration is going to decrease, producing colorless products. So you're going to see gradual fade of the color. The goal of the experiment is to determine rate law for the reaction, meaning numerical values for M and N, where M is order of reaction with respect to the dye, and N is order of reaction with respect to hydroxide. Now, I'd like to remind everyone that order of reaction with respect to a particular reactant is an extremely important parameter, which in general refers to this integer in the rate law, which would show how change in concentration of a particular reactant would affect rate. So if I changed concentration of the dye, I want to know how my rate will change, and M will tell me that. And if I change the concentration of hydroxide, value of N would tell me how the rate would be expected to be affected. So knowing M and N is a very important experimental question. So first, let's talk about finding M, order of reaction with respect to the dye. So here we're going to use what's called integrated rate law, which involves taking measurement of absorbance of our solution versus time. Now, why absorbance? A couple of weeks ago, we talked about so-called Beer's law. So hopefully you remember that absorbance of a colored solution is directly proportional to molar concentration of light-absorbing species. So in our example, dye, of course, is the one that absorbs light. So as reaction progresses, concentration of the dye is going to change, and hence absorbance will change. So we're going to be using absorbance as a means of testing concentration. So absorbance versus time is what we're going to be collecting, and that's what you're going to see reflected in the Excel spreadsheet once you get the files in the email. And then we're going to use absorbance versus time data to create 2 additional graphs. First one will be natural log of absorbance versus time, and third one will be 1 over absorbance versus time. And so that will be your job, to take raw data, which will be absorbance versus time, and then create 2 additional graphs. And then you're going to make scatter plots with each of the 3 data sets. You're going to obtain linear trend line, just like you have to do for the pre-lab that's due this week. And then you're going to get R squared value for each of the 3. And then you're going to look at the value of R squared and pick one graph whose R squared value is closest to 1. If R squared closest to 1 happens to be absorbance versus time, this will signify zeroth order reaction. If natural log of absorbance versus time happens to be the best linear fit, meaning R squared is closest to 1, then it would be first order reaction. And then of course if it's 1 over absorbance versus time that happens to be the best linear fit, then it would represent second order reaction. Now, when measuring absorbance, you may recall that we typically need to know what's called analytical wavelength. Analytical wavelength, just a reminder from our first lab quiz, analytical wavelength represents the wavelength where absorbance is the highest. The dye is purple, so it's going to absorb the most in the yellow range, and so wavelength is expected to be about 595 nanometers for this particular dye. I'd like to point out that I also included on Canvas under modules, I included several additional videos that I strongly encourage you to watch. Both videos are very informative and contain pertaining information and shows what the absorption spectrum for this dye would look like, what you would see on the screen of the computer if you ran the spectrum of the dye. So this next page basically explains what I already went over. So you're going to get linear trend lines, you're going to get equation of each line, you're going to get R squared value for each line, and then you're going to pick out the best linear fit, and based on that you're going to make your conclusion as to what the order of reaction with respect to the dye is. I'd like to point out that this has to be explained in detail when you're turning in your report for this experiment. So next we're going to talk about N, which is order of reaction with respect to hydroxide ion. And here we're using a very different approach. Hydroxide, of course, is colorless, and therefore we would not expect it to absorb light, so we have to use a different approach. This different approach is called method of initial concentration. We discussed this method briefly before you left campus, before break, and we talked about that method of initial concentration typically requires to do 2 trials of the experiment where concentration of the reactant in question would be varied, and then looking at how initial rate of such experiment would change as a result of the change in concentration of the reactant in question. So in our case, we're going to run 2 trials, and you're going to get 2 files, one for each trial. The difference between trials is concentration of hydroxide. Concentration of the dye is going to be the same for both trials. I will provide a procedure on Canvas. I'll post the procedure that you would be using. I'd like to point out that that procedure is different from the one in your lab manual in that we're using a Pascal spectrometer that takes readings of absorbance every second as opposed to every minute as described in your lab manual. So you're going to get data sets that are going to be big, anywhere between 120 and 200 data points, because the duration of the experiment is at least 2 minutes, meaning 120 seconds, or even a little longer. So going back to this, there are 2 trials, as you can see, trial 1 and trial 2. So the difference between the 2 trials, again, is the concentration of hydroxide. Now, I mentioned that concentration of the dye is 1.5 times 10 to the negative 5th. So you're going to, you would have been using same solution for both trials, same solution of the dye. So what about hydroxide? Well, hydroxide's concentration is going to vary. In trial 1, your concentration will be 0.1 moles per liter of hydroxide, and in trial 2, concentration of hydroxide will be 0.05 molar. So let's think about it, 0.1 molar versus 0.05 molar. It's clear that we are cutting the concentration of hydroxide in half, comparing trial 1 and trial 2. And so the assumption we're going to make is that initial rate can be found as slope of the best fit graph in the respective trial. So once you figure out which graph is the best linear fit graph, you can look at its equation and you can find the slope from the equation of the line, and that slope will actually give you the rate of reaction, whether in trial 1 or in trial 2. And then, as we talked about before, method of initial concentrations is all about making a ratio, where we're going to be dividing rate in trial 2 by rate in trial 1. And so we're going to use slopes of the respective best fit lines as a way of finding the rates. And here I wrote out the rate law for the reaction. So in trial 2, rate law can be represented as rate constant times concentration of the dye in the second trial in order of m times concentration of hydroxide ion in the second trial in order of n. And then this, of course, right here is the rate law for rate in trial 1. We still have rate constant. This is concentration of the dye in trial 1 in order of m times concentration of hydroxide in trial 1 in order of n. Now, looking at this equation, hopefully you can already see what we can cancel, what we can get rid of in this equation. Obviously, we can get rid of k, because k is independent of the initial rate, of the initial concentration. Now, the dye concentration, like I already mentioned, is the same in both trials. I showed you the bottle with the dye solution, and it would have been the only dye solution given to you in lab. And the concentration of the dye in the first trial is the same as concentration of the dye in the second trial, and it's equal to 1.5 times 10 to the negative fifth. And so we can cancel k, and we can cancel dye. So what's left is only the hydroxide. Like I said, hydroxide would be here, would be 0.1, and here it would be 0.05. So this concentration of hydroxide in the second trial is double of what you have in the first trial. So then, after we cancel the concentration of the dye in K, the ratio rate 2 to rate 1 would equal to concentration of hydroxide in the second trial in order of n divided by concentration of hydroxide in the first trial in order of n. Now, these are not the concentration that are going to be used in your experiment. So here you would have 0.1, and here you would have 0.05. But it's still obviously going to be 2 in order of n. And then to find the initial rates, you would use slopes of the respective lines. And then we can solve for n just like you did in the pre-lab, hopefully, by taking logs of both sides, and you have to show concentration of n. You have to show how you find n by solving that equation, taking logs of both sides. As far as data, I'd like to show you a couple of examples. My examples are going to be shorter type of data sets compared to what you will have, because these are all data that we got when we measured absorbance every minute instead of every second, so there's only 17 data points here. Your experiment would have taken a lot less time, but you will have a lot more data points. Like I said, usually we collect data for at least 2 minutes, which means 120 seconds, so you would have time in seconds here, and your time would go from, probably something like 1 second to 120 seconds. So this is absorbance, and the files that your TAs are going to send you are going to contain only time and absorbance. Your job is to create 2 more columns. One is natural log of absorbance, and the other one is 1 over absorbance. As I explained before you left for break, Excel allows you to do a calculation, and then you can drag down the cursor all the way from the first calculated point down to the last, and it will automatically calculate all these values for you. So then you're going to create 3 graphs for this particular trial. So your first graph will be absorbance versus time. Second graph will be natural log of absorbance versus time. And then third one will be 1 over absorbance versus time. So let's take a look at those graphs. So this is absorbance versus time for this particular trial. As you can see right up here, I have the equation of the line and I have our squared value. So our squared value for this particular graph happens to be 0.989. Let's take a look and see what other graphs give us. So this here is natural log of absorbance versus time. And as you can see, here's the equation, and R squared is 0.9997. Look at how close this R squared value is to 1. So far, this is our main contender for the best linear fit. But we still have to take a look at 1 over absorbance graph. So this graph here is 1 over absorbance versus time. And you can see the R squared value is lower than what we had in the previous graph. It's only 0.989. So out of the 3 graphs, which one do you think has a best linear fit? I hope you picked out the second graph we looked at, natural log of absorbance versus time. I'm going to go back to that one so we can take a look, and I would like to explain one more time why this would be the best linear graph. This is because our squared value for this particular graph out of the 3 we looked at is the highest and closest to 1 at 0.9997. Now you see the equation of the line that I also got? So what is the slope for this particular graph? As you can see, the slope is right here in front of the x. I can't quite reach. So for first trial, our slope of the graph of the best linear plot, which is ln A versus time. So this is best linear fit. And the slope is equal to negative 0.0515. So let's keep that information in mind. And I'd like to mention that I recruited my daughter, who is just like you, is a college student, and she's now back home from her college. So she is the one who is recording this, and I'm going to ask her to pen to that information over there on the board, so you guys can take a look at that. So now we're looking at the second trial. In the second trial, concentration of hydroxide is doubled compared to the first trial. Crystal violet remains the same. And so now we're looking to see how these graphs will pan out. Again, you're going to get information in your Excel file that will give you time in seconds and absorbance values. It will not give you these 2 columns. So natural log of absorbance versus time and 1 over absorbance versus time is something you're going to have to calculate before you can make these graphs. So once again, we're starting with absorbance versus time for this trial. We'll make it a little bigger. So our squared value for this one is 0.97. And you see I also got an equation of the line. By the way, notice how you should title your graph. So this one would be absorbance versus time. Remember, we always title the graph using y value versus x value. Dependent variable versus independent variable. So here's my absorbance on y-axis, and on x-axis I have time in minutes. You will have, here you will have time in seconds, and here you will have your absorbance for this first graph. The second graph is titled natural log of absorbance versus time. and it's helpful to show what concentration of hydroxide was used for that trial if you'd like. And then you have natural log of absorbance on y-axis. And you have time, yours will be in seconds. And of course you will have many more data points than I do in mine, because you're going to have absorbance measured every second rather than every minute. So looking at data for this graph, let me make it a little bigger. So up here you can see that R squared value for this graph is 0.987. If you recall the first one in this trial we looked at, it had R squared value of 9.97. So far this seems to be the better linear fit. And then the third graph, even without looking at R squared yet, you can tell these are the data points in yellow triangles, and it doesn't really look much of a linear fit, which is reflected in R squared value. So here R squared value is all the way down to 0.881, so this definitely is not the best linear fit. So out of the three graphs in this trial, which one would give us best linear fit? And the answer, of course, is it would be this one, because its R squared value at 0.9873 is the closest to 1 out of the three we looked at. Notice that in the second trial we got the same type of graph to be our best linear fit. If you recall, in the first trial our best fit line was natural log of absorbance versus time. And in the second trial, it's the same type of graph. This is exactly what you should see in the data you will be sent. So we need to know slope of our best fit line. In this trial, the slope is right here. So I'm going to write it down on the board here. So for trial 2, slope of natural log of absorbance versus time. This again is the best linear fit graph for this trial as well. And the slope is equal to minus 0.1285. So why do we need these slopes again? Because these slopes show us rate, initial rate value. This is rate 1, and this here is rate 2. So once again, once we found the two slopes, we can then try to solve for n. So here I'm showing the general setup, but I did not show the numerical setup. I'm going to go ahead and pull up the screen real quick so we can take a look at how math would work out if we use my data here and my slopes. So to find n, I would have to take rate in trial 2 and divide it by rate in trial 1. Rate 2 would be my slope for ln A versus time in the second trial, and my rate 1 would be slope of the same type of graph, but in the first trial. And that would give me, again, your concentrations of hydroxide will be 0.1 in the second trial and 0.05 molar in first trial. So, and this of course is an order of n. So 0.1 divided by 0.05 in order of n would give me 2 in order of n. And then I'm going to use the slopes. And I had minus 0.1285, and then I had minus 0.0515. So how do we solve for n from here? Again, we have to take logs of both sides and then find n. You can probably see that this slope is about twice this slope. In other words, this one is 2 times higher than this one. So n should be close to 1. But again, you must show work. Must show work. How you find n, meaning taking logs of both sides and solving for n. I would like to point out that your report should consist of 6 graphs, 3 graphs for trial 1 and 3 graphs for trial 2. Now, data sheets in your lab manual, I don't have page numbers. I guess I'll have to write you a note on that. I forgot to bring my lab manual here. So you only are responsible for the back of each data sheet. There are 2 data sheets in your lab manual. You don't need the table where you would record your time, your absorbance, and so on. You don't need that. You only need the back where you show which graph was the straightest line, the best linear fit, and how you find m and how you find n. Make sure to explain everything. More is better. There's plenty of room there on the back of the data sheet. So when TAs grade, they should be clear on how you're finding these things. This is it for now. I will be providing more information on Canvas under modules. Again, I hope everyone is staying safe, staying well, and is ready to start working in this new format. I'll see you guys later.